Welcome back, everybody. I thoroughly discussed the exam results in the previous video, but just to briefly go over it, first of all, there is a curve of 3. So add 3 to your score there. Also add your essay score to that, and that is your score out of 40. And on the upper left, you'll see a red number, a percentage. That is your current percent in this class. I will warn you that Friday is the last day that you can withdraw from a course without having to talk to me or the dean. After that, you can't even talk to me. You have to go to the dean. So just be aware of that. All right. We've still got 2 exams to go and some more extra credits. I did send out an email mentioning the current planetarium show on the formation of the planet Earth. It's a great show. And if you watch that and write a full 1-page double-spaced report on that and have it in by a week from Friday, then you will get the equivalent of an extra credit, which is 5% on a midterm exam, okay? And those can add up. Those can add up. I'm going to try and find some movies on YouTube that are educational, not just wowsy, and watch for emails on those as well. Anybody got any questions? Now, as to how to, I mentioned there's a big improvement, but what I see here is I know how many people are supposed to be here in this class, and I know a lot of people are watching the videos instead of coming to class. You want to do that, fine, but don't cry to me and come and say, Dr. Latta, gee, what can I do to improve my grade? The first thing I'm going to say is come to the real class rather than watch all the videos. Because I don't care how you cut it, being here live is a lot better. All right? But I'm preaching to the choir here because you're all here. All right? Okay. We are into the chapter on relativity. And the last lesson I ended by talking about inertial and non-inertial frames of reference. And instead of saying frame of reference, I will just say frame. It's just easier, okay? And the key difference between these 2 situations is that you're not accelerated in an inertial frame. It comes all down to acceleration. Over here, you are accelerated. And what happens in a non-inertial frame is that Newton's laws are not valid. Now, they really are, in the end, valid, but they appear to be invalid in a non-inertial frame. Classic cases, if the accelerations are large enough, as if you are in a car accident, I hope you never are, someone might say, I was thrown towards the windshield. I was thrown towards the windshield. Well, first of all, that's a huge acceleration, deceleration, whether it's a positive or negative acceleration is neither here nor there. But in a car accident, there's a huge acceleration, and we say that there's this force which threw you into the windshield or into the steering wheel or something like that. That's why you wear your seatbelt, so that the seatbelt will restrain you. But there is no force that really threw you into the windshield. What happened in real life was that the car stopped. You didn't, according to the law of inertia. You kept going, but to you, you were thrown into the windshield. Yet there is no rope or spring or electrical force or any other kind of force that's actually responsible for it. In inertial frames, Newton's laws are valid. And that is essentially how you figure out which one you are in. You perform simple experiments to see if Newton's laws are working, and if they are, then you're in an inertial frame. If not, then you are in an accelerated or a non-inertial frame. The key thing is here is you can determine which one you are in. In fact, the simplest accelerometer, if you want to know how you do it, if you simply take a ball and mount it on little springs in 3 dimensions, okay, up, down, left, right, and back, forth, and then you have some sort of electronic readout on that, if that ball should move at all, that means you're in an accelerated frame. And by measuring where the ball is and so forth, you can actually measure the acceleration. All right. Another example of an accelerometer is a seismometer. You don't think of the Earth as being accelerated, but they take essentially something that's very heavy on a light spring, and if it seems to move by itself, what's really going on is the Earth is moving, and the Earth is accelerating around it. It's not just moving. It has to change its velocity. So you can tell with an accelerometer which one you're in. So you can measure acceleration. It's relatively easy. Geez, now they have little electronic sensors that go in your phone, for Pete's sake. Okay? I got a couple of these in my shop at home. Now comes the $64 trillion question. Suppose you do a set of experiments, you get the most sensitive accelerometer you possibly can, which means you verify, you measure your acceleration as closely as you possibly can. And suppose you measure it, and within the ability of the device to measure your acceleration, because there's always a lower limit, right? And it says you're not accelerated. So you look at the accelerometer and it says you're not accelerated. Then you are in an inertial frame. So we can say you can tell which kind of frame you are in. You measure your acceleration. If it's 0, you're in this case. If it's non-zero, you're in a non-inertial frame. And the larger the acceleration, then the more non-inertial it is. Okay? You can't tell. Now, one of the huge questions, this is back in Newton and Galileo's time, was, is there a preferred frame of reference? We said that the frame of reference is arbitrary. You choose it to be convenient to you. But the question comes up, for instance, when you talk about the origin where the 3 axes overlap, a reasonable question is there a center of the universe? Is there a place in the universe that should truly be called the point 0, 0, 0? Well, as far as we know, there is no such place. There is no center of the universe. There is no center of the universe. There is no preferred origin. Another thing you can ask is, well, what about the orientation of the 3 axes? Well, without a gravitational field, there is no such thing as up or down. There is no preferred direction in space. So this means that there is no preferred frame of reference. There's no absolute, truly correct frame of reference. But it turns out, if it's an inertial frame, because Newton's laws are valued, this is the preferred type or class of frame. If possible, you want to use an inertial frame because then Newton's laws are valid. If you use a non-inertial frame, you still can work things out, but you have to change Newton's laws to account for the fact that it's accelerated, and that makes it harder. So we prefer to use inertial frames, but technically you can use any one you want that's convenient. It's just that weird things happen when you're in a non-inertial frame. You go out to the amusement park. Boy, I miss so badly going to Kennywood this summer and Cedar Point. I wanted to go to Cedar Point so badly, but there's no way I would go out and stand in line with 200 other people for a roller coaster. Just too dangerous, too dangerous. But when you go to these things, you get in these things that spin around, and you're with somebody else and you're outside, they're thrown into you, they're pushed into you. Well, that's actually one of the whole points of the ride. These rides originated 100 years ago when it wasn't appropriate to get too close to a lady or a guy, until you'd had 20 dates or something. But in one of those rides, you were forced together, whether you wanted to or not, and that was half the fun, but forced together by what? There is no force actually forcing you together. Centrifugal force is a fictitious force. You're not thrown out of the circle. You actually want to go straight, and the thing you're on wants to go turn. That's a non-inertial frame. So you can tell which one you're in, but we prefer this particular type of frame. But then we go further. So you can tell which one you're in. You can tell if you're accelerated or not. So suppose you are not accelerated. So suppose you determine I know. I yawn too. You can't see me yawn though with this mask on. Okay. Suppose you are in an inertial frame. So you measure your acceleration and you determine that it is 0. Now I ask you, and let's go even further. Let's go further. Suppose several people measure their system and determine that they are in an inertial frame. The classic situation is to suppose that we are out in space and we are in our spaceships and none of the engines of the spaceships are on. Why can't the engines be on? If everybody's in an inertial frame, can you have your engine on? The engine would cause what? A force, and a force would cause an acceleration. So none of the engines are burning. You don't have to keep those engines burning to keep the object moving. The law of inertia says it'll keep going. So there's another spaceship here, different spaceship. Somebody's on this spaceship. This person looks out and sees that spaceship moving. This guy looks out and sees that spaceship moving. And suppose there's someone else on some other kind of spaceship. And they're moving. But none of them has their engines turned on. None of them is in a gravitational field. Everybody is out in free space. But I look out and I see that ship and that ship moving. They look out and see the other ships moving. But here's the question. Who is really moving and who isn't? If you make it even simpler, if you just have two people approaching each other in their spaceships, here's the other one coming in. This person sees the other one approaching. This person sees the other one approaching. It could be that one of them is sitting still and the other one's coming in, or it could be that this one is sitting still and the other is coming in, or they could both be doing this. We look out and we see galaxies coming towards us. but are they coming towards us or are we going towards them? So everybody's in inertial frames. In every case here, they are in inertial frames. But they're moving with respect to each other. And you ask the question, who is moving and who isn't? What we find back in the time of Galileo and Newton is that there is absolutely no way to resolve this. No way. If you are in an inertial frame, you cannot determine absolutely your velocity. If you are in an inertial frame, you cannot absolutely determine your velocity. Now, since you're in an inertial frame, your acceleration is zero. So whatever your velocity is, it's not changing. This is what we're saying. So you say, okay, my velocity, whatever it is not changing, but what is my velocity? The answer is you cannot tell. So, what does it feel like to be in an inertial frame? If you can't tell what your velocity is, your velocity could be zero, which means pretty much when you are in an inertial frame, it feels like you are not moving. It feels like you're not moving. Now see, if you're accelerated, if you're in a non-inertial frame, you can't determine your velocity anyway because whatever it was, it just changed because you're accelerated, see? It doesn't make sense to say, can you absolutely determine your velocity in a non-inertial frame? Because whatever it is, it just changed because you're accelerated. You either sped up or slowed down or changed your direction. It's a pointless question. But if your acceleration is zero and you're in an inertial frame, you cannot absolutely determine your velocity. Which means you might as well not be moving. You can assume you are at rest. And nobody can prove whether you are right or whether you are wrong. This person can say, I am not moving, you two are. This person can say, no, I'm sitting still, you guys are moving. This person can say, no, I'm sitting still, you guys are moving. Or they all could be moving, right? There is no way to tell if they're all in inertial frames. This was very unsatisfying. Like I can say, well, is the earth moving and does it feel like it's moving? Do you feel like it's moving? No. No. I could sleep right now. Just fine. Okay, I could sleep just fine. Yet I know the earth is turning on its axis and I know the earth is going around the sun. So I know that the earth is going with respect to the sun. Is the sun moving? We don't know. We don't know. We look out and we see other stars approaching us or receding. Imagine this is the whole planet. We see stars out here approaching us or leaving or receding from us. We can measure that by looking at the light from the stars, by the way. That's how we can tell. Okay? But the question comes, well, are they approaching us or receding from us, or are they sitting still and are we doing the moving? You can't tell. If you are in an inertial frame, you cannot absolutely determine your velocity, which means you can't determine whether you're moving. You can't even determine if you're moving. And since you can't determine if you're moving, you can assume that you are sitting still and nobody can argue with you or prove otherwise. This is a profound philosophical idea that comes out. You cannot absolutely determine whether you're moving. If you tell you're not accelerated, fine, but then you say, am I moving? I don't know. So I might as well assume I'm at rest. Being in an inertial frame, for all intents and purposes, feel like you are at rest. Any questions there? So an example, if you're on a nice smooth train going at constant speed in a straight line, and you close the windows, you can't tell if you're moving. Question?
How do we determine the velocity of the Earth then?
We can look at the sun and measure, we can tell that the Earth is changing its position because we can look at the stars and the sun. And we can tell how long it takes to go around, and we can form a giant triangle with the sun and stars and figure out what the distance to the sun is. And knowing that we're going approximately in a circle and how long it takes, we can work out how fast we're going. It's about 67,000 miles an hour.
How about the sun, and we determine that it's moving?
We cannot. What we actually do know is that in most galaxies, all of the stars are orbiting around the center, and so we are in the Milky Way, and so the sun is moving. But the absolute velocities are different because how do we know? You're assuming that the velocity's doing, or the galaxy's doing this, but how do you know it's not moving sideways as well? You see, these are the problems. And this is a major problem. You can assume you're at rest. It's unsettling. I don't like it. I ought to be able to tell absolutely if I'm moving. Well, according to Newton and Galileo, you cannot. The detection of absolute motion is impossible. And guess what we're going to find in the end, Tyler? Guess what we're going to find?
What?
You can't determine absolutely if you're moving. This is the final and be-all result.
So is it possible to say that the sun moving is a theory then?
As a what?
Is a theory then?
No. We know it's moving relative to other things.
Okay, just want to know.
But we can't tell if they're moving. See? Follow me? It's always relative velocity. Now, here is the exciting thing. When electricity is discovered and magnetism is discovered, and guess what we're going to be studying? Electricity and magnetism. When electricity and magnetism come to be understood, the possibility suggests itself that perhaps we can absolutely measure velocity. So another way of summarizing this, there is no, so according to Galileo and Newton, there is no preferred or absolute frame of reference. This is another way of saying that you can't determine absolutely your velocity. Preferred kind of frame is the inertial frame of reference. But among those, there are infinite numbers of those. There is no single one which is hell and high water above everybody else. But when we come to understand electricity and magnetism, it gets very exciting because the possibility suggests itself that this is wrong. So, electricity and magnetism in the late 1800s, early 1900s suggest that the above statement may be wrong. So this is very exciting. Obviously, I can tell, Tyler, you don't like this idea, and lots of people didn't like it. We should be able to tell if the sun's moving or if the earth is moving and all this.
I don't hate the idea at all, I'm just wondering what that means.
Well, a lot of other people were wondering what it means too. That's the whole point. So I say I don't like it. It seems to me I ought to be able to do it. All right, so this means we're going to take a look at electricity and magnetism and see where it comes in that this might be wrong. In the end, we're going to come full circle and find out that this is true. And then the question comes in, if this is absolutely true, then we are going to see that we have to revise how we understand mass, and how we understand time in particular, and how we understand distance. That proving that this is actually true, first we think it might be wrong, and then ultimately in the end we come back and say, gosh darn it, it's true, but then there are repercussions of this being true as to how time behaves and as to how distance and mass behave. Now, electricity goes way back. To study electricity, we go back to the Greeks. And the Greeks found that if you took a piece of amber, amber is solidified tree sap. Solidified tree sap. What movies does amber play a big part in? What movie franchise is amber very important? Jurassic Park. This is where they supposedly get the dino DNA. Well, we really can't do that. But let's face it, it is fun to see dinosaurs go out there and gobble people up. That's what kind of makes those movies great, okay? Amber is solidified tree sap. It's considered kind of a mineral, and you may not know that they make jewelry out of it. Okay, very fine amber makes beautiful jewelry. Well, the Greeks discovered that if you rub this with wool, or rabbit fur, or some kind of fur, that if you rub it, that you discover that the amber will attract bits of hair and other fur to it. In other words, for you ladies, static cling. Okay? Nothing worse than you get yourself ready to go out. This happens with guys too. You get yourself all brushed off, and your kitty cat comes up and gives you some love, and you're covered with cat hair. And it sticks all over you. And it's a devil to get off. That's what we're talking about, static electricity. The word electric is Greek for amber. Electric is the Greek word for amber. Okay, that's where it comes from. Okay, so we call this static electricity. Now I can try to demonstrate this. I don't know how if I'm going to succeed or not. But what I have here are two fine little floats. All right, like that. And what I'm going to try to do is to take a piece of plastic. Plastic is the modern equivalent of amber. Rub it with modern fur. I don't know if this will work. It depends on the humidity. And yes, you can see that these are sort of pushed away. Let's try and do it. I think this plastic thing will work even better. We'll find out. But if there's any humidity in the air, it tends to mess it up. There we go. Notice that they're pushed away from the plastic, and they're also pushed away from each other. And what's remarkable is that if I touch them, and if I touch the object that I've rubbed, I don't know if that'll work right or not, that for the most part the effect goes away. Let me try rubbing the glass. Everybody's gotten a spark when they get out of their car in the wintertime, and it's just evidently we got too much moisture here. We've just got too much moisture in the room. Oh, it's just not cooperating. I think, what was the best? This one was the best, wasn't it?
Yeah.
This one was the best. So it's not going to cooperate today. If you observe it carefully, they're not behaving like they should. What you find is that first they're drawn towards it and then they're pushed away. And after they touch it, they're pushed away from each other. So rubbing this thing gives it something. And that evidently things that have that something repel each other. Okay? One of the problems here is cloths and stuff carry, there we go. They carry chemicals on them that are designed to eliminate this effect. That's part of the problem. You put fabric softener on your clothes with anti-stat in it to stop this from happening. You don't want your dress or whatever to draw that cat from, okay? But it appears that if you touch a rod, charge it up, and then touch it to something, that something is pushed away. Okay? And what is remarkable is that this is plastic. If you then take that very same ball and don't let it discharge, and you bring it near a rod that is made of a different substance like glass, it is attracted to it. Whatever this force is, it can be repulsive or attractive. This indicates that there are at least two different kinds of charge. The kind when you rub plastic with the cloth, and the type that you get when you rub glass. And clearly, since both of these have the same charge, like charges repel each other, but then opposite charges attract. It is possible to rub the glass with the cloth, let the bob touch it, so that some of the charge transfers, and then it's repelled. So experiments show that there are two kinds of electric charge. Positive and negative. You could have called them black, white, up, down, green, red, I don't care. But Benjamin Franklin, I believe, is the one who decided to use a plus and a minus sign to represent the two kinds of charge. Positive and negative. Plus and minus. Now, it's easy enough to tell. You simply say, okay, I'm going to say that when I rub the plastic with the wool, I'm going to call that positive charge. And one of the things we see is that like charges repel. If we have a positive charge and a positive charge, they are pushed away from each other. Likewise, if we have two negative charges, the two negative charges are pushed away from each other. However, if we have a negative and a positive charge, they are pulled towards each other. Opposites attract, like charges repel. So opposite charges attract, and like charges repel. Experiments have been done to see if there's a third kind of charge that behaves differently than this. But in all the experiments that have been done, only two types of charge have been found. And in fact, we know right now that normal matter which we call neutral matter, contains tons of charge, but it's in balance. It's balanced. And what happens when you rub the object so that the glass contains equal numbers of positive and negative charges, and so does the rag. When you rub this, you can actually transfer electrical charges from one to the other, leaving an imbalance. It turns out it's usually the negative charges that get moved around, but not always. So when I rub this, I actually transfer negative charges from one to the other. Having too few negative charges means you have an excess of positive. It means you're positively charged. Having too much of the negative charge means that you have too many and you are negatively charged. So what actually happens here is you transfer the charge from one to the other. Experiments will show, and they discovered this right away, that not only does the rubbed object become charged, but the rag does too, with the opposite charge. So when you rub them together, you separate the charges and you produce an imbalance, and you get too many negatives on one and not enough on the other, positive, negative. Change to a different kind of fabric, and it might get transferred the other way. It just depends on what we call the electronegativity of the thing. We're not going into that. The point is that you can move the charge around, and like charges hate each other's guts, and opposite charges attract, like charges repel and hate each other. So how many people have done this? You shuffle your feet in the wintertime, you rub your feet against the carpet, then you find your little sister, and then you go shock her, and then she runs screaming to mom, you know, Greggy shocked me, blah, blah, blah. What I'm doing is I'm building up a charge on me. All those charges hate each other, and my little sister's there. Well, hey, here's a place I can go, and they do. And they have a spark. It actually jumps. The charges can move. That is going to be of key importance. The charges can actually move from one place to the other. Bryce, what's the biggest spark you've ever seen?
Biggest spark
The
ever?
biggest spark you've ever seen. You see it all the time in the summer.
Go ahead and say the sun.
A spark, electrical spark.
Electrical spark.
Instantaneous, quick spark makes a tremendous sound.
I like it.
Lightning. Lightning. Lightning is the same thing. Benjamin Franklin showed that lightning is actually electrical in nature, and the same phenomena that he saw in his laboratory is just happening with lightning, but on a much larger scale. You don't transfer a charge between here and the cloth. You transfer charge from one part of the cloud to the other, and if the charge gets out of balance enough, you get enough negative charge in one part of the cloud, it hates each other's guts, right? And over here is a bunch of positive charge of which it loves. What's going to happen? they're going to leap. And when they leap, they produce tremendous heat, which heats the air, and that gives you the thunder. And of course, you hear that, and they also produce tremendous amounts of light, and they can also produce a huge amount of heat. It is totally possible for a spark, instead of jumping a quarter of an inch between me and my little sister, to jump 2,000 feet from a cloud up there down to the ground. 2,000 feet, 3,000 feet, if there's enough of an imbalance. And that is what light is. Let's stop right there and let us do the quiz.